I would like to start this talk with a story. So the story starts with a grad student named Evan, who's in this room today, who approaches me and says, "Hey David, I would like a project. Can you help me, can you give me something to implement?" And so I'm a theorist. You can see here, here's a picture of me being a theorist. It's totally accurate. And I'm a theorist asking about graph algorithms. And so when he asked me for something to implement, I said, yes, there's actually this beautiful algorithm by Angua and McGregor, and it solves the dynamic streaming connected components problem. Evan, being an inquisitive guy, asks me, why do you want me to implement that algorithm specifically? And so for a second, I take off my theorist hat and I put on my system builder hat, because while I am fundamentally a theorist, I'm interested in figuring out how to make algorithms work in practice and help people out. And so the hope for this algorithm is that it could allow us to analyze massive and changing graphs, even when they're much larger than what we can store in RAM. So I'm going to give a little bit more detail on this story and then get into what happened after. So first, I just want to define this problem that this beautiful algorithm solves, which is the dynamic streaming connected components problem. And this is a little theory for a second, and then I get into some fun system stuff. So in this problem, our task is to find the connected components of a graph with endnodes. And this graph is subject to a stream of edge insertions and deletions. So I've got an example here where we start off with a toy graph. It's just 5 nodes, and it has no edges to start. And then our input stream could tell us, for instance, let's insert an edge between nodes 2 and nodes 5. So we add that to our little picture. Maybe next, it tells us to insert an edge between nodes 2 and nodes 3. And notice how we're keeping track in the bottom here of the connected components as we go, right? And at the end, it says the last update in our little toy stream tells us to delete the edge between 2 and 5. So at the end of this, perhaps we're queried for the connected components of this graph. And so, of course, for this example, we'd say 2 and 3 are connected. Everything else are just disconnected little islands all on their own. The thing that makes this problem challenging and that makes the algorithm to solve it interesting is this extra constraint, which we call a semi-streaming constraint, which says that we only have n times polylog n space to compute this, which is much less, potentially, than we would need to store the entire graph explicitly. So that's the problem that we want to solve with this algorithm that I'll now say just a little bit about on McGregor's algorithm to solve this problem. So they solve this problem by using a technique called linear sketching, which allows them to compress the graph stream using very small space, in this case, n times log cubed n. So we've got a little picture here where we see we've got a graph, and then our sketching algorithm is compressing that. And the nice thing about this little data structure, this sketch data structure, is that it's very small, and even though it compresses our insert and delete updates one by one in the order that the stream gives them, that's all it can do, it recovers the connected components with high probability. With high probability here indicates that this is a randomized algorithm, which is an important detail here. But it's really nice. This is much less space than we would need to represent some graphs explicitly. And finally, when I say that the graph is useful and that can help us do this, what exactly do I mean? What is the promise of this? Why should systems people care about this nice theory algorithm? Well, the promise of this semi-streaming connectivity algorithm is that it allows us to handle massive graphs. Because the space complexity of this algorithm is so small, we can handle larger graphs given the same amount of space compared to a technique that must store the graph explicitly. Existing systems, such as Aspen and Terrace, which appeared in SIGMOD last year, which solve similar problems, streaming graph problems for databases and for other purposes, these all choose to store the graph losslessly, which is good for many applications, but in our case, we want to compress further to get the best scaling we possibly can. And there's an extra prize here, which is if we can get this algorithm to work, this connected components algorithm is a black box for many other algorithms that have similar, really powerful scaling properties. So it would be really nice if we could make this happen. So excited, Evan and I and some other students all get together and we start designing our plan for this system. But very quickly, our excitement gets slowed down a little bit when we realize the data structure we're going to build is actually going to be quite large. A little back of the envelope calculation. Remember I said before that the space complexity of this algorithm is n times log cubed n. So let's just imagine what n times log cubed n, ignoring the constants, what that would be for a graph on, say, 1 billion nodes, which is a reasonably sized graph that we might want to compute on. Well, it turns out that before constants, plugging that in, this requires roughly 25 terabytes of space. So asymptotically, we know that this is small, and of course, there are many graphs on 1 billion nodes that would be much larger than this to represent explicitly. This is still a very high random cost. And so Evan very cleverly asked, well, can we come up with a better algorithm, asymptotically reduce the space cost to do something better? And we were excited about this for a little bit until we found a paper by Jelani Nelson and Hua Cheng Yu just a couple of years ago that said, no, actually asymptotically, this algorithm is optimal in terms of space. So at this point, we were feeling pretty dejected. This lower bound was a dark cloud over our heads. And as far as we were concerned, the RAM requirement for this algorithm might as well have been infinity RAM. So our question was, how can we get around this lower bound to produce something useful? So this talk is not entirely sad. By the end of the talk, I'm going to tell you how we built a system that solves the dynamic streaming connecting components problem for critical use case. So the sun's peeking out from the clouds, we're not so sad anymore. And to do this, we've designed an algorithm which manages to work well, despite the space lower bound, which seems to be so problematic. And so by the end of this talk, I hope to convince you that these techniques in the semi-streaming world offer a useful solution to these massive graph processing problems. So what do I mean by useful? Because useful can mean a lot of things. Well, I'm going to be very specific for the purposes of this talk. Useful means three things. First, for an algorithm to be useful, we have to be able to run it on today's hardware, right? Otherwise, what are we doing with it? And so in this case, the key word here is space. As I just mentioned before, this lower bound means that this algorithm appears to require a lot of space. How can we get it to run on modern systems? Second, because we're trying to deal with graphs that change over time, perhaps very rapidly, speed is also very important. Can we keep up with high-speed data streams and still give an answer to our question? And finally, a useful system meets a need that nobody else is meeting, ideally. And so when can existing systems find the connected components for large and changing graphs? So a key word here is density. And I'll get more to that in a second. These three words, space, speed, and density, together they'll make a useful algorithm that can actually help us in the real world. I'm going to start by talking a little bit about density. So our algorithm uses n times log cubed n space, right? And notice how this complexity scales with the number of nodes in the graph, but not the number of edges. So this means that we offer the greatest gains when e, the number of edges, is large, i.e. the denser the graph gets, the more space we save. Now, there's a commonly held belief in graph processing that some of you may have heard, some of you may believe, which is that large dense graphs don't really exist in practice. Whenever we deal with large graphs in the real world, they're always sparse. And indeed, existing systems such as Aspen and Terrace, like I mentioned before, optimize for the special case of processing sparse graphs. And so I would like to ask, of course, sparse graphs and processing them are extremely important, but I would like to ask the question, I'd just like to raise the question, is it really true that they're the only game in town? So I'd like to show you a plot. This plot shows us graph data sets from the network repository. So each orange dot on this plot is a graph data set. Its position on the x-axis tells us how many nodes it has. Further to the right means more nodes. Its position on the y-axis tells us how many edges it has out of all possible edges it might have. So higher up means denser. So we can see that for graphs with a small number of nodes, we see that these graphs exist at a variety of densities. Some are very sparse, some are very dense. But as the number of nodes increases, we see that the graphs get sparser and sparser until they're just this very tiny slice of the overall problem space that we see. Now you may be saying, well, David, it seems like this plot exactly proves the point of the conventional wisdom that there are sparse graphs out there. And indeed, I can say, yes, that is one interpretation of this plot, but I would like to suggest for a moment another interpretation. I've drawn this black line here, this curved black line, which splits the plot into two regions. Everything to the left of this region are all the graphs that you can represent explicitly in less than about 16 gigabytes of space, which I chose semi-arbitrarily. Everything on the right side requires more space than that. So we can see that all the existing graphs are the sort of graphs that we can represent in a relatively small amount of space, the sort of thing that would easily fit in RAM. Everything that could potentially exist on the right side, but we don't really see here, are things that would be more inconvenient, harder to process. So there's a question, why is this plot empty? Is it because there's really nothing there, or because we don't have the tools to analyze it? Well, in fact, we do know that there are things in that inconvenient section of our plot. For example, VLDB 2015 paper, Facebook engineers talk about working with very large, very dense graph data sets. Tens of millions of nodes, hundreds of billions of edges. And the only way they were able to do this was at great cost on enormous supercomputing clusters. So maybe that's fine if you're Facebook, but if you're anybody else, and maybe somebody who's more prone to sharing your data, then probably if you have a data set like that, you just decide to think about it some other way or give up entirely. So I would like to propose that this is probably a selection effect. We lack the tools to study large and dense graph streams, so they're very rarely studied, and they're not published. So I'd like to raise the question, rather than only focusing on sparse, special purpose graph processing systems, what could we do with a more general system? What sort of applications would we be able to do? I know it would help Facebook. Could it help other people as well? We see lots of evidence for these sort of dense data sets that are just proprietary or too valuable for people to share. In any case, that's all I have time to say about density for now. But I hope I convinced you that it's an unmet need that we can explore. So now I want to say a little bit about space and speed and how we overcome those challenges to make a useful algorithm for this problem. So remember I talked about this sketching algorithm before, and then we were all sad, and that was because we realized that space complexity is actually rather high for many graphs that we would like to compute on in practice. Constants are large, and the asymptotics are just such that it is often going to overflow random in practice. That's a space concern. We also have some speed concerns. It turns out that this algorithm, just out of the box, for processing a graph update or answering a query, these things are very slow, very computationally intensive. And what's even worse is that if your data structure is going to overflow RAM, you might be tempted to go out of core. But that's even worse. Because this algorithm is randomized, it's going to be making random accesses out of core all the time. This is extremely slow, basically unusable. So it should seem like the sketching approach is just useless in general in practice. But it's actually not. So we came up with a much better sketching algorithm, which we call cube sketch. So you can see here now the little sketch artist has a cube for a head. And I can't tell you all the details about cube sketch in the time we have available, but I'll give you the highlights. So it's able to process updates 3 orders of magnitude faster than the best existing algorithm for this. Uses 8 times less space. And most interestingly, it's IO optimal in the external memory model. So this is how we get around our space issue. Even though we don't have enough RAM necessarily to store our data structures, we can make our algorithm such that it runs quickly in external memory without sacrificing performance. And I'll prove that later experimentally. And lastly, we still retain our space optimality. We don't get rid of that from the original algorithm. So these steps allow our algorithm to be much more practical. Using that, and this is finally where we get to your question, we built our system which we call GraphZeppelin. The tagline for this is avoiding the data explosion in graph streams. And so there's this famous Zeppelin called the GraphZeppelin, which was the first aircraft to circumnavigate the globe, and very notably, it was not the Hindenburg and never exploded. So that's the story behind that name. And so GraphZeppelin is both fast, it can handle high-speed streams, and it's compact. By fast, we mean on a single modest scientific workstation, we were able to process 3 to 5 million updates per second when our data structures resided in RAM. And when we forced those data structures to live on disk instead, it could still handle 2.5 million updates per second. By consumer SSD here, I mean I went to Best Buy and we just bought some SSDs off the shelf. This was not fancy hardware, and we were still able to get this performance. It's also compact. In one experiment, we were able to compress a stream that was more than 200 gigabytes in size down to a sketch that was only 45 gigabytes in size. So I'd just like to say a little bit comparing this to the current state-of-the-art solutions in graph streaming. Again, these are Aspen and Terrace, which I mentioned before, and these systems are optimized for sparse graphs. So we're going to test them on a variety of graphs, including graphs that are quite dense. And what we found here is that on dense graphs, GraphZeppelin is more compact than these existing systems. For graphs up to several 100,000 nodes, it ends up being about twice as small as Aspen and about 10 times smaller than Terrace. And this trend we expect to continue as we consider larger and larger graphs. Remember, GraphZeppelin is asymptotically much smaller than these other systems. We found the crossover point. Beyond this point, for suitably dense graphs, the gap in space is only going to increase. Similarly, it's faster on these dense graphs as well. We saw that when we kept the data structures in RAM, it was twice as fast as Aspen and over 30 times faster than Terrace. So here we see this plot. This is log scale. You can see how as the size of graphs increases, the gap in speed between GraphZeppelin on the top and Aspen on the bottom increases. And I just want to note again that Aspen and Terrace, these systems are optimized for sparse graphs. And so in their own papers on different hardware, they report 10 to 50 million edges per second, which is significantly faster than any of these systems got on these dense graphs. But in the more general case of dense graphs, GraphZeppelin is faster. And then when all of these systems keep their data structures on disk rather than in RAM, we see that, okay, for each of these, we see these circled points where the respective systems went to disk. We see that Aspen and Terrace, these are the 2 dotted lines, at the points where they go to disk, their ingestion rate drops drastically. This is a log scale graph. And that GraphZeppelin only takes a minor hit to performance at that point. And again, this isn't a dig on these other systems. They're not designed for out-of-core computation. That's the sort of thing that you have to do to really compute at scale. And so it shows that GraphZeppelin is more robust in that setting. So I just want to say a tiny bit about future work here. One of the things that we'd like to do is these linear sketching data structures that make up our system are CPU intensive, but they're also very easily distributable. So in some follow-up work, we're looking at moving the CPU work and dealing with it on a cluster or perhaps a GPU. We'd also like to improve the query performance. Currently, the queries are comparable to the existing best systems, but we think with better algorithms, we can improve them significantly. And finally, remember I mentioned way back at the beginning of the talk, part of the promise of this system is that this connected components algorithm is a black box for lots of other interesting graph properties. So we hope to build out that toolbox very soon. With my last minute, I'd just like to say a couple of takeaways, both as a theorist and then as a system builder. So first, my little theory thing is that I think we should be including I/O bounds for the semi-streaming algorithms we make, for the streaming algorithms that we use for graph systems, because as this work shows, these data structures are often not going to be able to live in RAM. So they have to work well in the external memory model as well. And beyond that, we should be optimizing their running times, and not just for space, as is typically the case in the streaming setting. And the prize, if we do these things, is graph algorithms that are useful in a practical sense right out of the box. The gap between theory and practice can be very small. And then finally, my takeaway on the system side is to say that we should embrace dense graphs. We should study them, we should design systems to analyze them, rather than focusing on this vanishingly small special case of sparse graphs, which is still very useful. And the last takeaway is that graph sketching is useful now, and that we should consider it and other lossy graph compression mechanisms if you care about scaling and processing truly massive graphs. So if we do these things, I am confident that we'll be able to process much larger graphs than we ever have before. Thank you.
Thanks a lot. I think you answered my question.
Yeah.
Yes.
Hi, that was a fantastic talk, thank you. So regarding that sparse versus dense, I found it very interesting. So I have two questions on that. First of all, how does GraphZeppelin work or perform on sparse graphs? So is it then a Hindenburg or is it still a Zeppelin? And second is, what graphs did you evaluate on? Because your observation was that there are no large real-world dense graphs. So what did you use for your evaluation?
Great question. I'm going to answer these questions in reverse order. So,
Yes.
so your second question, which was what graph data sets do we evaluate on? So we started from the Graph 500 specification. It has a specification for Kronecker graphs, and we just use that to generate denser Kronecker graphs than people normally use, and that got us to the level of density we wanted. So that's how we handled that. We wanted to do something that we hoped would be a little bit more structurally realistic than, say, a simple error-shrinking graph, which you can make arbitrarily dense, but maybe it's controversial how often those appear in practice. So we tried to go for the existing benchmark that was as realistic as possible. And sorry, could you repeat your first question again?
The first question is how it performs on sparse graphs. So did you also evaluate on sparse graphs?
Yes. Okay. So as I pointed out earlier in the talk, in terms of space, the space doesn't change depending on whether the graph is sparse or dense. So if your graph is very, very sparse, the data structure for GraphZeppelin is going to be larger than just representing it explicitly. So if your graph is sparse enough, GraphZeppelin isn't the right approach because it's pretty large. However, its ingestion speeds are almost completely independent of how sparse or dense the graph is. So that at least stays consistent. And there's some question of whether in future work we can take advantage of that in some ways.
Sorry, I even have a third question. Do you think there is a way to unite these two worlds, or is it too much specialized on sparse or on dense? Because all the systems are just specialized on sparse, you specialize on dense, but then we have even more systems for different sorts of graphs, not even for different sorts of workloads, but even depending on the graph itself. So that could also sort of, like split the systems world even more.
Yeah. I think this is a really exciting question. We've only started thinking about it. I think that there is hope for doing this, but it's probably the sort of thing that is theoretically quite complicated, and then the engineering is quite complicated about that again. So I think that's good news, and I'd love to work on it with whoever's interested.
Great, thanks.
Cool. Thanks a lot. Another round of applause, maybe? Great.